Alright, this is my video on aseptic technique in culturing microbes. Here's my card here. The date is May 24th, 2023. Let me move my hand that way the course ID is totally seen. My name is Zachary Bush. Now, this assignment obviously was later than I intended it to be turned in. That was entirely my fault, and I accept full responsibility for that. The reason that it was turned in late was because this past week I had finals going on for all my other classes, and I had to go down to my college to complete those finals. And because of where I live in such a remote location, when I go down to my college, it's generally a day-long trip, and I have to spend the night. And because of all the finals I had to do, I ended up having to spend about half the week away from my house and away from the experiments. Obviously, that's something I should have planned for, something I should have taken into account before I started this experiment, and there's no excuse for it. And I apologize for this whole video and all my lab report being late. There's no excuse for it, as I said before, and I apologize. But let me get into the results of the lab. First thing I'll get into is the yeast. As you can see, there's the round cultures there, the circular cultures. I wasn't shocked by how the yeast turned out, given that I just did agar plates with yeast in a very similar experiment earlier in the week, and turned out to be a very similar shape and size. So there was no real shock with the yeast. The number of yeast colonies that I saw, not shocking due to the dilution, and there was nothing real shocking about the yeast. It started growing around the same time as the E. coli. The SE grew much faster than everything else. Not sure why that is. My guess is it can probably handle colder temperatures better than the yeast and the E. coli, but that's just a guess, as I'm wondering whether my workstation is just a bit too cold to work effectively, and I'll have to buy something to incubate my cultures. Now for the SE, this was the fastest growing culture and was by far the most visible. This culture, it has circular shapes and it has spindle shapes. These shapes range from but the sizes range from pinpoint to large, and I really wanted to show that in my data because I thought it was important to show all the sizes, all the shapes, and all the variations that this one bacteria could show. Moving on to E. coli. E. coli, as you can see here, there's some very small dots ranging from about pinpoint size to small size, and there are about a dozen of them. Again, this culture took much longer to develop and much longer to really show that it was growing. And yeah, this one took about as long as the yeast. Again, why I'm thinking that my workplace is a bit cold and I might need to buy an incubator. Now, all in all, this experiment, I think, aside from the fact that I didn't submit it on time, went fairly decently. There wasn't a lot of hiccups, again, other than the timetable, and I think I would call this experiment a success. As far as real-world usage, streak plates can be used to determine whether a bacteria is contaminated. When you use a streak plate, for instance, let me use SE here. When you use a streak plate, as you can see, there's one color and pretty much one or two shapes here, right? Now, if I did a streak plate and all of a sudden I had something very brown and in a irregular shape, that would be a very clear sign that my sample was contaminated and I needed to fix that. So that's something that streak plates can be used for in real life, and that is the end of this video. Again, I apologize for this coming in so late, and there's no excuse for it.